Okay, we're looking at the last two pages from exam 3 of general chemistry. This is covering chapters 6 through 9, and the last two pages are both covering Lewis structures and molecular geometry and how to draw these structures. Excuse me for just a minute, I've got to adjust my microphone there. So when we're looking at Lewis structures and molecular structures, there's a systematic way of doing this. And the most common mistake that happens is steps get skipped. And when you start to skip steps, you increase the chance that, you start to make a mistake along the way. What usually happens is that we start to make some assumptions about how the geometries are supposed to look or how the Lewis structures look, and then when you make those assumptions, you lose something along the way. I'm not saying that there aren't shortcuts that exist. I'm just saying before we know when we can apply the shortcuts, we got to spend some time in this also, right? So basically what I'm saying is whenever I ask you to draw a Lewis structure or a molecular structure, don't skip any steps for now. When you guys get to organic chemistry, then you guys will start to learn some of the shortcuts, but shortcuts can only be applied to very specific places, okay? All right, what we can start to see though, I should make say a caveat here before we get into it. What we can see is not necessarily a shortcut, but patterns, right? Patterns of how certain atoms behave, how many lone pairs things tend to have, how many bonds things tend to have. That is something that is useful to pay attention to, all right? So as you're going through and doing your practice, pay attention to patterns. Don't try to find shortcuts necessarily, if that makes sense. But anyway, right, no shortcuts for what we're doing here. Let's step through it systematically, right? Step one, we got to know our number of valence electrons, right? Step one is figure out your total number of valence electrons. We have 4 from carbon, 2 from the hydrogens, right? 2 from the hydrogens, I mean 1 from each hydrogen for a total of 2, and then 14 from the chlorines total, right? 7 from each of them. Right, so we have a total of 20 electrons here that we have to deal with. Okay. Step 2, right, we're going to do our skeletal structure. I'm just going to move this out of the way for just a minute because it's getting in my way here. So I'm just going to write that over here for now, and then we'll move it out of the way. Okay, so skeletal structure. That means we put the least electronegative atom in the middle, right? And then we attach everything. Right, our skeletal structure means we attach everything to that central atom with single bonds. Now, why didn't I put hydrogen in the middle? Well, remember, hydrogen will never be in the middle of a Lewis structure. It's only ever going to have one bond to it, so it'll never be in the middle of anything. And that's one of these patterns that I mean, right? It's not a shortcut to say that hydrogen's on the outside. It's a pattern, right? So if we know how to use those patterns, then we can kind of simplify some of these things, right? But I'm getting a little bit off topic here. All right, so we have a carbon in the middle, and we draw our skeletal structure in step 3, right? We're filling in lone pairs, and we fill in lone pairs, right, from highest electronegativity to lowest electronegativity, okay? So from high to low, from the outside in, from the highest electronegativity to the lowest. We've used a total of 8 electrons already, right? We've used a total of 8 electrons already for the 4 bonds in green there that you see, right? So we've got to fill in our rest of our 12. So we've got 8, 10, 12, 14, 16, 18, 20, okay? The most skipped step. The most skipped step. I always ask you guys, make sure you're checking yourself there, okay? Make sure you check yourself when you're done drawing your first Lewis structure. Otherwise, it's very easy to make some mistakes. Now, what are the important checks to follow? Check to make sure, right? Check to make sure that you didn't use more electrons than what you started out with. All right, we started out with 20. Let me just write this in green here so we can color code this. right? We started out with 20 total electrons. We used 8 electrons to make our 4 bonds in green, and we added in 12 in our lone pairs there, right? So we have a total of 20 electrons. The next most important step is to do our formal charges check, okay? Now, formal charges check, there's a formula you can use for it. I tend to use the magic science circle, as I call it, right? In magic science circle, you cover the atom, you cut through the bond. So you have 1 electron coming from the bond, 2, 3, 4, 5, 6, 7, okay? You have 7 electrons that are in the circle. And chlorine comes in with 7 valence electrons. So valence minus circle, okay? So valence minus circle electrons is going to get you your formal charge. What color is this? We'll do it in purple here. Okay. So we've got a formal charge of 0 for that chlorine. Magic science circle, that cuts the bond in half. So 1, 2, 3, 4, 5, 6, 7, right? 7 in the circle. Comes in with 7 valence electrons, so formal charge of 0. 4 in the circle for the carbon. It comes in with 4 valence electrons, formal charge of 0. And if you, I think we can do the hydrogen in our head, right? It has 1 electron, comes in with 1 electron, with 1 valence electron, so formal charges of 0 and 0. So everything's got a 0 formal charge. Okay, and that's what that's not bad, right? I'm not saying that everything has to have 0 formal charges, but that's kind of one of the ideal cases that we have, right? We normally, if we have things that have 0 formal charges, that's a good sign for us. We don't want to have any unusual formal charges, right? So that might look a little bit busy, but it's important. You gotta go through and check, okay? You gotta go through and check. So good, that looks like a nice Lewis structure. Now, how do we deal with molecular structure? Well, molecular structure, you just have, there's a certain part of it that you have to memorize. If you have a central atom, right? Remember we call that atom A, right? And we can have 2 things around it. Okay? And we use this ax notation, where the central atom A either had lone pairs or other atoms around it. So if you had an ax notation of AX4, right, where we had a central atom with 4 other atoms around it, right, that's tetrahedral. If you have 4 total things around a central atom, the only thing it can ever be is tetrahedral. Right? If we have 4 atoms, it can only ever be tetrahedral, okay? So we got to draw a tetrahedral geometry. So let me move this out of the way. So how do we draw a tetrahedron? Well, we can put a carbon in the middle, and tetrahedrons are always going to be looking something like this, right? Some derivative of this. And then we just plop our hydrogens wherever we want, and our chlorines wherever we want, right? It's not going to make a difference for here. And fill in our lone pairs. Good stuff. And then we're done. There's our nice, beautiful, perfect pièce de résistance, right? Our molecular structure. And so we ask, what's the molecular geometry? Molecular geometry for this is going to be tetrahedral also. So tetrahedral. Remember, our molecular geometry is looking at how many atoms are around the central atom. Okay, how many atoms are around that central atom? We don't care about lone pairs for a molecular geometry. I'm not saying that the lone pairs don't affect the geometry. It's just when we go to naming them, we don't care about it. Okay, it's just when we go to naming it. All right. So let's clean this side up over here, and we can move on to the next one. We're going to follow the exact same steps, right? The exact same steps. Total number of valence electrons, 6 from the sulfur, 28 from the 4 fluorine, so a total of 34 electrons we have to deal with. Sulfur goes in the middle. We connect everything. with our skeletal structure. Okay. Let's track electrons as we go along. So we've used 8 electrons so far. 8 electrons so far. So we've got 26 more electrons that we have to deal with. All right. So we add lone pairs, right? We add our remaining electrons from the outside in, from the most electronegative atoms in. So we've got 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So where are we going to put that 34th? Well, 34 goes around that central sulfur. Okay, you can't violate the octet rule for fluorine, but sulfur, no problems. Okay, sulfur can handle those extra electrons, so we're going to put that around there. So there it is. Okay, we can go through and we can check our formal charges. I'm going to zoom in here just to double check here. Okay, 7 in the circle, 7 valence electrons. So a formal charge of 0 on the fluorine. And now here's where we can start to look for those patterns, right? Hopefully, you can see how each fluorine in this structure is identical. And so if they're all identical, that means that each of the formal charges is going to be the same. Oops, I meant to do that in purple. All right, so if the formal charge here is 0, then this is going to be 0, 0, and 0, okay? Let's check out our sulfur. 1, 2, 3, 4, 5, 6. 6 in our circle. Comes in with 6 valence electrons. So formal charge of 0 for our sulfur also. Fantastic, right? So everything's 0. Pretty good sign that we've got the correct Lewis structure, okay? We go think about our axe notation again. We've got 4 atoms and 1 lone pair. So we've got a total of 5 things, right? We've got a total of 5 things around that central atom. And if we have 5 things around our central atom, it can only ever be a trigonal bipyramidal. Okay? It can only ever be trigonal bipyramidal. Now, trigonal bipyramidal is one of those weird ones where you have to pay attention as where we put that lone pair. The lone pair in the trigonal bipyramidal is going to be in one of the equatorial positions. Let me erase that for a second. The equatorial positions are here, here, or here. Right? Lone pairs around a trigonal bipyramidal structure are going to go into the equatorial positions. So pick one of those, it doesn't matter which, and put it there, right? Oops, I'm sorry, I should do these in green to stay consistent. There it is, okay. So let's just put our lone pair here. Then we can fill in the rest of this. Fantastic. One of the finest looking molecular structures I've ever seen in my life. Now, as a quick point, right, you'll see some people draw it like this, and you'll see some people draw it like this, where you put the lone pair directly next to the sulfur. Technically, this way is correct, let's say more correct to put it here in this fashion. It doesn't really matter to me whichever way you guys want to do it for now. You know, I kind of write in both ways. The reason why I show you guys this way is because remember, I told you guys that if you know the 5 electron pair geometries, right, then you can just substitute in whatever you want to around those atoms. And so you have to know those 5 structures, then you can just fill in whatever you want. So it's just kind of a shorthand way of doing it. I'm not going to be that picky about things, right? Either way is fine. But anyway, so there is our molecular structure with the proper geometry. Now, our molecular geometry, the name of this, is when you have 4 atoms and 1 lone pair around a central atom This is our seesaw, right? This is our seesaw. All right, moving right along. To shorthand it, we've got 12 total electrons here. 6 from the sulfur, 4 from the carbon, 2 from the other hydrogens, okay? We put our least electronegative in the middle. Least electronegative in the middle. Sulfur, let's do that in blue. Sulfur, hydrogen, hydrogen, right? So we've used 6 electrons so far. So we fill in the other ones. Okay. And now we have to go, right? Now something's wrong about this, right? We've used all of our 12 electrons already, right? 6 coming in the green there and 6 coming in the red, right? But there's a problem. The problem is this. The carbon right here is violating the octet rule, and carbon's not going to violate the octet rule. So we have to give it some extra electrons. So how we're going to do that is we're going to plop a nearby lone pair into a double bond, okay? And so the correct Lewis structure at the end of the day is going to look like this. We have a double bond there. Oops, sorry. We have a double bond there. Fantastic, right? And so there is our correct structure. If we go through, I'm going to quickly go through it, just I don't want this to be a 3-hour long video. Everything's going to have a 0 formal charge in this case. Now here's some good practice. Here's some good practice. Prove to yourself why this is not the ideal. Right? Prove to yourself why this is not the best Lewis structure. I'm going to give you a hint. You got to do your formal charges. So go through, check your formal charges for that one boxed in black there, and tell me why it's not the best formal chart. The best Lewis structure. Okay. All right. So continuing on with the one in blue, right? We have a ax notation of AX3, right? So 3 things around that central atom. That means we're trigonal planar, right? And if we're trigonal planar, this is one of our easier ones to draw. Right. The tricky part about drawing a trigonal planar is make sure that you have a an angle here of 120, right? Sorry, I didn't mean to put a theta there. So just make sure you draw as best as you can a bond angles of 120 here. Remember, molecular structure, the whole point is to show, right, as best as we can, what the actual structure looks like. Okay? Perfect, wonderful, beautiful, trigonal, planar, molecular geometry, right? All right, O2F. O2F is always a tricky one because this is where people tend to skip steps, right? We got 20 total electrons, and we have to draw the Lewis structure. Now, you put the least electronegative atom in the middle, right? Oxygen. Oxygen is the least electronegative. Then you connect it up, right? Connect it up to fluorine here, and another oxygen on this side there, right? Fill in lone pairs. Sorry. Fill in lone pairs, starting from the most electronegative. Okay. Start from the outside in. Fantastic. Right. Okay. So I'm going to pause here. Right? I'm going to pause here and give you guys a second to pause and say, well, check to make sure that, you know, this is a proper Lewis structure here. Check to make sure that this one's better than the most commonly, let's say, incorrect answer of this one here. Let's box this one in black, right? The one in black is incorrect. The one in blue is better, okay? From the rules that we know, let me make with that caveat, right? From the rules that we know, the one in blue is going to be the better structure, all right? So go through and figure out why. So take a quick second. And when you come back, I'll have the answer for you, right? Right? So I quickly went through and I looked at the formal charges, right? The formal charges for the two compounds here, right? The one on top, we've got a negative charge on the oxygen. That's not too bad, right? Oxygen's pretty electronegative. It's not happy having a negative, but it's okay with a negative. But the one at the bottom, right? We've got two negative charges, a positive charge on a fluorine, just a very unusual count for our formal charges, okay? Fluorine with a positive formal charge, you better have a very good reason for it to be doing that, right? You're really never, in fact, off the top of my head, I can't ever think of a situation where I've ever seen a fluorine with a positive charge, a positive formal charge, okay? So the reason why the one on top is going to be better for us is because, right, we minimize our formal charges, right? Minimize our formal charges, and we do not have a plus on our fluorine. So let me just erase this abomination here so we don't get confused. All right, so that's what we're going to be working with. Okay, axe notation, 2 atoms, 2 lone pairs, okay? We got a total of 4 things. We got a total of 4 things around our central atom. That means we're dealing with tetrahedron. So we got our oxygen, right? We set up our generic structure for a tetrahedron. We can fill in lone pairs wherever we want. We can put our oxygen or our fluorine in the front or the back. That doesn't matter. And then we draw the world's best oof molecule. Okay. 2 atoms, 2 lone pairs. The geometry, the molecular geometry is going to be bent. And I'm going to break this video here because this one's getting a little bit long. So here's the second page, excuse me, the third page, and in the next video we'll wrap this up.